All right, I think now we are live. All right, so we're going to read this paper. The unified picture of ionic redox in lithium sodium ion batteries. And let me check what I have summarized in here. Yeah, so this is the name of the paper and a brief summary of the paper. This paper proposed a unified picture for understanding the irreversibility of oxygen redox in A-rich. So A means the alkaline metals like lithium and sodium. So lithium and sodium rich transition metal oxides. Basically, this means that transition metal oxides can be layered structures, like one layer, another layer, another layer. And in each layer, we have the lithium layer, we also have the transition metal layer. And for the lithium rich, basically means that in the transition metal layer, we replace the transition metal with lithium. And that is called the lithium rich transition metal oxides. And they're going to use the electron localization function to locate the oxygen lone pairs. So oxygen lone pairs basically means that the lone pairs, which means that the electron pair that is not connected with other. So oxygen have like two lone pairs. So for each oxygen, it has two lone pairs. I guess here I should say something about this. 16. Okay. So the electronic structure of oxygen is one s 2, 2s2, 2p4. So if we only consider about the valence electron, which is this 2s2, 2p4, that leaves us two lone pairs for each oxygen. And each oxygen needs to be bound into like two different metals. So the charge transfer gap or the charge transfer gap between transition metal oxides. So this concept, I need to really understand it while reading the papers, because I think this is a very important concept that we need to realize. It's proposed as descriptor to quantify the amount of extra capacity achievable and its reversibility in discharging process. So the amount of extra capacity achievable basically means how many oxygen atoms can be. So this basically means can be oxidized during the charging process. So charging process means that we're losing lithium in cathode. How many oxygen atoms? Because the transition metal, when it can be reduced or oxidized, it can give electrons. But we want to give more electrons. Then those electrons can only come from the oxygen in there. That's why we call it the oxygen redox, because oxygen can be oxidized and it can be reduced. All right. Conclusion is that the reversibility of ionic capacity is limited to holes per oxygen. So holes basically means the number of electrons that is taken away from the oxygen. So if I take away one electron from oxygen, this means I create a hole like in the oxygen atom, and it's less than 1/3, which means that for each oxygen, the maximum amount of electron that can be taken from that oxygen and still maintain its reversibility is 1/3. Let's figure out how they drawing up this conclusion. Right, so for the introduction, yeah, so for oxygen redox, what we want from it is to increase the capacity. But because when you oxidized oxygen, it turned to like rearrange itself. And if two oxygen combine together in order to form like oxygen dimer, it will break the oxide structures. So by holding the structural stability is really hard. This one reversible, okay. Yeah, okay. Let's check on this. Check on, yeah. So here's the paper that we're going to read. Okay, finally, X implies some conventional 1+2 number and transition metal, which may lead to unfavorable situations where transition metal become more electronegative than the ions. Okay. Cationic MM substitutions. MM substitutions. So MM substitutions are levers to increase the number. So one way to increase the number of lone pair is to make substitution. Levers to increase the number of lone oxygen to p pair. Okay, as a robust criteria, we consider that all metals forming peroxide phases have strong enough reducing powers to prevent, thereby increasing N. Such substitution might be seen as AA rather than MM, as they lower the material's total capacity when A is not equal to A prime. Okay, so we need to figure out what is A, what is M. So we are going A rich TMO. So transition metal is M. Oxides. Catonic vacancy. Okay. Such substitutions might be seen as this rather than this, as they lower the material's total capacity. I'm sorry, I don't understand this. So red basically means I don't understand. Cationic vacancies also increase N. Cationic vacancy. So if we create a cation vacancy, this means we oxidize some oxygen due to charge balance. We need positive charge, the negative charge should also decrease. Yeah. And if there's no more electrons on there, okay, how can it increase N? So what is it? N is the number of lone pairs. All right. All right, let's really understand this. This is important. Okay, so lone pairs. I mean, up to now, oxygen lone pairs. So in this section, they are talking about the number of oxygen lone pairs. And we need to figure out how many lone pairs, how many oxygen lone pairs is actually in here. The chemical formula of A-rich transition metal oxides is this one. Yes. Okay. The number of lone pair can be calculated using the octet rule. Assuming each oxygen is 4 pairs of electrons to be stable, yeah, we don't need N as the average number per oxygen. Cation ordered phase. Assuming each oxygen is 4 pairs of electrons to be stable. Why? Yeah, I know this sentence, but 4 pairs of electrons. Oxygen already have, so it will attract like 2 electrons. Okay. So I mean, if okay, so in here, I'm going to like using, no, it's way too small. Okay, I'm going to do that in here. Calculate the number of oxygen entropy. All right, how do we think about this problem? Is to increase the number of chemical formula for HTML is, let's see, is this one. If it is charge balanced. If it is charge balanced, the oxygen will have oxidation states -2. All the oxygen will be a thick octet group. Then for each oxygen, it will have 2 lone pairs of 4. So for oxygen ion, if it's oxygen ion, then it's 4 lone pair. Am I right? If n is an integer for x equals 0, okay, how does this work? If, let's see, if x equals 0, okay, when x equals 0, it's AMO2. So when does lone pair, when does the number of lone pair can be? Okay. Can oxygen doesn't have an octet rule? I don't think so. Okay, so they think that's the universal octet rule. So basically means that the number of electrons in the lone pair plus the number of the electrons used for bonding equals 8. Okay, let's write it more mathematically. An electron plus electron bonding equals 8. So basically means one is the number of electrons in the lone pair, and this one is the number of electrons in bonding. So one is a lone pair, one is bonding. And we know that n equals no, 2. Because lone pair, because each lone pair has this. Then I think the question would be, how do I calculate this one? So how many electrons actually bonding? So x equals 0 is this one. I don't really understand this. Does anyone familiar with this one? Canonical vacancies also increase, and this is explains why. Lone pairs of oxygen. Two bonds and two lone pairs. In layered general formula, the average number of this per oxygen is directly linked to the X stoichiometry. Stoichiometry, which also says the catonic this. Okay, this is. But what is okay? So lithium is +1 and this is +3. Lithium is +1, is +4, and his +7. Are you kidding me? In this +7. Okay, let's assume m is +3. Okay. When x equals 0, let's assume this is our examples. This one. Then both oxygen both oxygen connects to nickel and lithium. It's oxygen -2. Which means the number of lone pair. But how do they determine whether it's ionic or how to decide whether the bond is ionic or covalent? So how do we decide? Okay, let's just assume. Okay, let's assume. Assume ionic bonds. So oxygen 2-, which means bonding is 0. and this one equals 8, and we know that n equals this equals 4. Yeah, so in this case n equals 4. When x equals, let's see, when x equals 1/3, we have what? We have a, and we have a 1/3 and 2/3. This is clearly charge imbalance. This is charge imbalance. And so the positive charge. So the positive charge will be positive charge will be 1/4(3) plus 3/2(3). Okay, so here's 2. There's 2, and here is so 3. So basically it's 3. Yeah. This is the charge. And negative charge. So for each oxygen, oxidation state is minus. Equals minus this, minus this. And why the lone pair in this? For each oxygen, the oxidation state is this one. Then how can the number of lone pair is integer? Mm-hmm. 0. What? What's the definition of this lone pair? Okay. Oxygen, okay. Oxygen S. And this one? Zero. Why is it 0? Oh, okay, I see it. I see it. Okay. All right. So, indeed, it's the energy level of oxygen transfer so I don't discuss it. This leaves us 3 molecules. This leaves us 3 lone pairs in the oxygen. If x equals 0, this means each oxygen forms 3 bond with the transition metals. So that's 0. If next form 2 bonds, transition metal 10, so it has 1 lone pair. If x equals to 7, each oxygen will only form 1 bond. Now I understand this. So basically, it's so the number of lone pairs. The number of lone pairs n is equal to 3 minus the number of bonds. For all right, so this is something, and if x is not equal to them, which means if x is not equal to 0, a third or 2/3. This means that we are dealing with something. That means we are dealing disorders. The disordering basically means is disorder. We're dealing with disordering here. And so if x is really, really large, then for some oxygen, it will not bonded. Oh, so in here, I think they have an assumption. The oxygen will be bonded with transition metals covalent. This is a very important assumption. This is very important. The oxygen will be bonded. Okay. The chemical formula for HTML is this one. Okay, assumption. All right, now I can understand this. Levers. Okay, so when we understand this, we know why increase the number of lone pair. This is because we will change and we reduce the covalent bonds between this increase. This increase the number of lone pairs, and also, yeah, cationic vacancy is the same. The number of lone pairs, yeah. This explains why ionic redox can be activated in materials showing no A excess. As long as they have holes, it will be fine. Or post-transition metal. This is invariant with the substitution ratio. be lithium-rich nickel in its cobalt. The ionic capacity increases with Y due to the electrochemical activity and not to the increase of N. Okay, let's say ionic. Ionic activity. Okay, let's read. From now on, we will term an oxidation process involving this. Compare. Oxidation process involving whether the states participate in the electrochemical activity depends on the material ground state. According to what is this? TMOs can be applied into two categories. One is not harbored and the other one is charge transfer. So, what is the difference? Okay, let's see what this means. Band gaps and the electronic structure. Right. So this is the basically means Mount Harbor is u less than what? What is u? Coulombic interactions, MO charge transfer. Okay, MO charge transfer basically means the energy level of oxygen to here. Okay, some terminology. Delta is the gap between the levels in oxygen and Luma in transition metals. And U is the gap between HOMO and LUMO in transition metals. Now what is W? What is W? Okay, W is the width. Okay, so there are two cases. If delta is less than U, what? Maybe this is different. Let's see. Okay. Let's say they're neutral. Figure 3. Okay, let's just keep going. Don't. The electronic regime defines the amount of capacity available. How the ionic process and is the first important criterion to consider when investigating the electrochemical property. Oh my